Good morning everybody, and welcome to this week's YouTube video, which is a worked exam answer video where I'm going to be looking at a buffer calculation whereby we have prepared a buffer solution and then we have added a small amount of an alkali to the buffer solution, and we are having to calculate the pH of the buffer solution after the addition of the alkali. Now, my last two YouTube videos have been a part 1 and a part 2 of a mastering buffer calculations with Miss G, where I've had a look at how we can prepare buffers and how we can then work out the pH after addition of a small amount of acid or alkali to said buffer solution. So it may be, if you haven't yet watched those videos, that would be a really good place to start, because I'm going to be using the same approach to answer this question as I have done in those videos. So if you think that this is helpful and you want to learn more, have a look at those videos that are up on my YouTube channel now. Or if you think it would be helpful to watch those videos first and then come back to this worked example and see if you can follow it along with me a bit more easily, having watched those already, that might be another good thing to do. So I've highlighted the key information here, but what I'm then going to do is I'm going to write underneath in the same colours that I used on those two YouTube videos all of the information I'm then going to need to answer this question. So in part 1 of the aforementioned videos, we had a look at how to work out the pH of a buffer solution by using the value provided for Ka, the acid dissociation constant, by using the moles of the salt and the moles of the weak acid. Now, we haven't been asked to calculate the original pH of the buffer solution this time, but I've still written those three values down because when we then add an alkali or an acid to our buffer solution, as was covered in video part 2, we need to know how the moles of the salt and the weak acid are going to change. So we need to know what they are initially, and we were given the moles of the salt straight up, so that was nice and straightforward. And then for the moles of the weak acid, we were given a volume and a concentration, so I've just multiplied those together with the volume in decimeters cubed to get the moles. And then what we would have done had we were calculating the pH of the buffer solution is write our Ka expression and then rearrange that to get the concentration of H plus equals. And as I explained in part 1 of the video, I always use the moles of the weak acid and the moles of the salt. So when I rearrange my Ka expression to get the concentration of H plus equals, I drop the square brackets from these two here because I'm going to use the moles. And of course, as soon as we've got H plus, we can get pH, because pH is minus log base 10 of the hydrogen ion concentration. So we don't need to actually do that, but we're going to need this expression in a moment once we've worked out how the amount of moles of the salt and the amount of moles of weak acid are going to change when we add this amount of potassium hydroxide. So we need to think about how the position of equilibrium for the weak acid dissociation is going to move and what that will do to the values for these moles. So that's what I'm going to do next. So the question tells us that we're adding 3 times 10 to the minus 4 moles of potassium hydroxide to our buffer solution. And when we do that, the hydroxide ions from the potassium hydroxide react away some of the H plus ions and form water. And thus, if we have a look at our weak acid dissociation equation, when we lose H plus ions because they're being taken away to react with the OH minus, the position of equilibrium has to shift to counteract or oppose that change. That's what Le Chatelier explained. When the position of equilibrium shifts to the right to replace the H plus that's been used up in the reaction with the OH minus to make water, we're going to lose some of the weak acid because that's going to dissociate to replace the H plus ions. But that dissociation also generates X minus ions, which means that the amount of our salt is going to increase. So as I did in the videos, mastering buffer calculations with Miss G, I've got a little decreasing arrow here to show that the moles of weak acid is going to decrease, and then I've got a little up arrow here to show that the moles of the salt is going to increase. And the amount that they will decrease and increase is the same as the moles of the potassium hydroxide that we added. Because these all react in a 1-to-1 ratio, that many moles of KOH i.e. that many moles of OH minus from the KOH, will react with that amount of H plus. So that's the amount of H plus that then needs to be replaced. So that's the amount of HX that will dissociate, and that's therefore also the amount of X minus that will be made. So taking the moles of the salt and the moles of the weak acid that we had initially, we can make those changes. So the moles of the salt is going to increase. So I took the initial moles and added on the 3 times 10 to the minus 4. And then for the weak acid, I took the initial 0.05 and then I took away the 3 times 10 to the minus 4, and that gave me the new moles of the salt and of the weak acid. Then it just becomes a case of subbing it into the rearranged Ka expression that I used up here and using Ka that we were given in the question. So the concentration of H plus ions is Ka times by the new moles of the weak acid divided by the new moles of the salt. Then once we've got the H plus concentration, we do minus log base 10 of that to get our pH, which is 4.30. And what we would learn if we worked out the pH of the buffer solution initially is that this pH will be nigh on identical. We would say that the pH of the buffer has been maintained upon addition of this small amount of alkali, because the ratio of the weak acid to the salt has stayed almost constant, meaning the concentration of the H plus ions has also stayed almost constant, allowing the pH to be maintained. As I say, that's the approach I used in the mastering buffer calculations with Miss G videos. So if you think that it'd be worth a watch of those, please head to my YouTube channel and you'll find them there. If you've got any questions about the approach used here or on the videos, please do reach out via a comment on this YouTube video or through any of my other social media platforms, or please feel free to drop me an email and I would be more than happy to help. Thank you so much for watching. Hope you all have a really good day.